Hi guys, welcome to Python tutorial, and in this video you are going to learn Python bitwise operators. So bitwise operators are used to compare binary numbers. So these are some of the important bitwise operators. So first one is AND, OR, JOR, NOT, left shift and right shift. First we will see AND bitwise operators. So if you remember in previous chapter, in previous videos, I have showed you that AND operator is normally used when both the conditions are true. But in this case, in this bitwise AND operator sets 1 if both the bits are 1. So let's see with example. So here A has 12 and B 4. So now if you print here A and B, so now let's see. So here I can see it's 4. So how 4 is displayed here? Let's compare her. First let's find the binary number of 12. Here let's enter 12 and then convert. So you can see the binary number of this 12 is 1100. Now let's paste here. So it's 1100. Now let's find the binary number of 4. So let's type here 4 and then it is 100. Now let's 0. Now let's add here. So it will be 0 and then 0. This 0 and this 0. So here will be 0. Here 2, 0 and then again 0. So it will be here 0. So 1 and 1, it will be 1. And here actually it is 0 before. So 1 and 0. So it will be 0. So now the output is 1 0 0. So as you know, this 1 0 0 is the binary of number 4. That is why it is displaying here 4. Now the next one is OR operator. So this OR operator is normally the pipe sign. So in this case what happens, sets 1 if any one of the bits are 1. So as you know that OR operators, in OR operators what happens, if any one of the conditions is true, then it becomes true. So here also if there is 0 and 1, then it returns 1. So let's see with example. So here let's copy it and then rather than this let's put here OR. Now try to run this code. This time it's 12. So how? Because now let's put it again here. So this is the binary of 12 and this one is binary of 4. Now put one more 0 to make it equal. So in case of OR operator what happens, it will be 0 here. Let's put it like this. So this is 0, this is 0, so it will be 0 and now again 0, and this one also 1 and 1 0 1. Because in OR operator if any one of the number is 1, then it becomes 1. But in case of AND bitwise operators, if any one both should be 1 only, then it returns 1. But in case of OR bitwise operator, here if any one is 1, in that case it returns 1. So here it is 0 and then 0 and 111 and then 101. So it is, the result is 1100. So as you can see, 1100 is binary of 12. That is right, it is returning here 12. Now let's see the JOR and XOR operator. So what happens is this: set 0 if both are same and 1 if both are different. So you remember here, if both are same, in that case it becomes 0, and if both are different, in that case it becomes 1. So here in our case, the JOR operator, here it will be if both are, then it will be, so here in this case both are same, so it will be 1 and then 1 and then 0 and then. So as I mentioned before, that if both are same, in that case, if both are same, in that case it returns 0. So here in this case our numbers are 1 1 0 0, and below is 0 1 0 0. So if you see here, these two are equals, so it will be 0. Here also 0, and then these two are of same type, so this will be also 0. These two are different, okay, so here it will be 1. So here the output will be 1000, this one. So if you convert this one, let's go to here and convert this 1000. So if you convert this 1000, then you can see here the decimal number is 8. So that is why it will display you. So let's run this. So but before that, I'd like to recap this so that there is no confusion. What happens here, if both are of same types, then it returns 0. So this one is same type, then it returns 0. This one is also same type, then it becomes 0. This 1 and 1 is also same types, in that case it becomes 0. But this one 1 and 0 is different, that is why here is 1. So total is 1000, this one. And when you convert this decimal into binary into decimal, then you will find that the output is 8. So that was JOR operator or XOR operator. Now the next one is left shift operators. So what happens in this: shift left by pushing 0 in from the right and let the leftmost bits fall off. So I think unless you see the practical example, it is difficult to understand it. So let me show you that how this will work. So if I write here B2, so what will happen here, or let it B4, okay, B4. So what will happen, 4 extra 0 will be shifted to the left, okay, 4 extra 0, because this one, so 4 extra 0, that means it will be 1 2 3 4. So if we shift this to left side, so our initial value was this one, okay. So if B left shift A left shift B, that means 4 extra 0 will be shifted to the left. So 1 2 3 4. Now so it will be this one. Okay, so now if you try to convert this binary into the decimal number, then see the result. Let's comment this outlet and go to here, paste here the decimal number, and when you convert this, oh, there is something wrong. It should be robust actually. Swap. No. So you can see the output is 192. So let's try to run this one. And press enter, you can see this 192. Similarly, if you put this 2, okay, so in this case what will happen, 2 extra 0 will be shifted to elapsed, so the 2 extra 0 will be removed from here. Now let's again copy this one and convert here from this one to this. There is some error, there will be no this one actually. So you can see it is 48. Now run here also and press enter, you can see the output is here 48, because in this case what happens here, only 2 extra 0 is remaining here. So let me recap this again so that you have a better understanding. Okay, what happens, the binary of 12 is 1100, right? This is the binary of this one, and then 2 extra 0 will be shifted from left side. Okay, that means we can say added. Okay, so it will be 11 then 40. Okay, and when you convert this 11,000, then you will find the output as 48. So that's it about the left shift operator. And each against this, as each reverse to this, there is right shift operator. So in right shift operator, what will happen, if you see the previous example closely, then what happens, 0 is gained, but in this case, in the right shift operator, 0 is lost. Okay, so in this case it will be 1100. This is the binary of this 12. Now extra 20 it will lose, so here extra 20 is lost, so it will remain only 11. So here you can see it is displaying 3. Now let's copy this 110 and then paste here. You will see, oh, in a second, there will be actually no, there will be 2, it will lose 2 zeros. See, it is already 1100, sorry, this is 1100 and 2 extra 0 will lose, so it will be only 11, not 1100 actually. So here 110, it will be 11. So here you can see 3, same result is displayed here. You can see same result is displayed here. So for recap again, what happens in case of left shift operator, 0 is gained, 0 is shifted from right to left, but in case of right shift operator, 0 is removed, you can say in another word, or the 0 is shifted from left to right. So 0 is lost here, not gained. Okay, so hope you understand this left shift and right shift operator. And the last one is this tilde operator, shift operator. So how does it work? As it says that inverts all the bits. So let's see with our example here. So if we do something like this, the tilde operator, then I'm writing here say 2. Okay, simply let's do this B. Okay, tilde B. So B has 2. Okay, now if we try to run this code, then you will see it is -3. Isn't it weird? Yeah, of course it is. So why it is displaying -3? So remember that negative numbers are stored as the 2's complement of the positive counterpart. Remember, in machine, minus is never stored. It is stored as a positive, not negative. So as an example here, the representation of -2 in 2's complement is 8 bits. So it will be 1 1 1 1 1 1 1 1 0. So how it will be like that? So let's get back to here and type 2 and then try to convert it. It is this, no, it has this number. Okay, so now here for 4 extra zeros, and here this one is 2's extra complement. Okay, binary signs 2's complement. So now this 10 will be, so here will be 10 and then 1 2 3 4. So now when we will revert it, so it will be 1 0 1 1 1 1. It will be something like this. But if you convert this as add bit, then it will be, its inverse will be like this, 2's complement. So 2 starts as 0 0, this 0 0 0 0 0 0 and 10, and by inverting the bits we get 1 1 1 1 1 1 and 0 1. Okay, because in tilde operator we get the inverse number. Now adding 1 gets us the result above. The first bit is the sign bit implying a negative, the first bit. So let's take a look at how we get tilde 2 equals to -3. So flip all the bits to 1 1 1 1 1 1 0 0 and add 1. Remember here, add 1 to become negative value -3. So now it becomes 1 1 1 1 1 1 and 0 1, because we added 1 extra to represent as a 2's complement for a negative number. So if you simply invert the bits in 2, you get the 2's complement representation of this -3. Now we will try to convert this 12. Okay, so here rather than A, let's write here B. Here this time we are passing as A. So let's see the result. Now compile it and you will see, oh, it's not saved, that's why it's displaying this. You can see it is displaying -13. So how it came -13? Now let's find the binary of 12. So let's find the complement of this 12. Okay, let's go to, and then you can see this is the complement of 12, 1100, and this is 2's complement. Now copy it, and for implementation I'm pasting here, and then now let's add 4 extra 0, 1 2 3 4. So our number is 0 0 0 0 1 1 0 0. Now if we will revert this number, then it will be 1 1 1 1 0 0 1 1. So the question is how we will store this minus 13. Remember, in system you cannot store minus number. First you have to convert this minus number into positive, and then you can store into the system. But how that can be achieved? It can be achieved through 2's complement. It is called 2's complement. And there is a formula for that: tilde n, then tilde tilde n plus 1 equals to minus n plus 1. So as you can see here that 1 is added extra to get this 2's complement. For example, here n is 10, then 1 0 1 0, then 0 1 0 1, so and ultimately this one is plus 1 and 1 is achieved here with this formula. So basically the xn is complement and not a negation. Here x equals to tilde x produce results minus x plus 1. So always x equal to tilde 12. So 12 plus 1, that means minus 3. Sorry, minus 13 will be one I missed there. So the binary format of this 12 is this one. So to find its complement, we will just reverse this number 1, then 1 1 1 0 0 1 0, and then again add here 1. Okay, here 1. So in this case it will become now 1 1 1 1 0 0 1 0 0 and here 1. So this is the 2's complement. So this number is actually 2's complement of minus 13. So that means this one is this represents the 12. So this one is 2's complement of minus 13.
And now if you compare this number with complements of 12, they are same, and that's why you got